Okay, welcome to the afternoon session. Our first speaker is Pierre Roux from University of Oxford, and he's going to talk about nonlinear, non-local Fokker-Planck equations modeling networks of integrated and fire neurons at the mesoscopic scale. Please.
So thank you very much. Thanks to the organizers for inviting me and for you for attending my talk. I hope to be able to talk about kinetic equations, but unfortunately, I wasn't fast enough to learn to work on them. So this will be a parabolic equation, strange parabolic equations, but still a parabolic equation. So I hope you will tolerate this before your eyes. We will talk about these electric buoys today, which are in all of your brains and are involved to you listening to my talk. And they have a strange structure where they have these tree-like things, which we call dendrites, and these things, axons. And the axons are connected to the dendrites of the other neurons. And basically, it's how they communicate. So you have a phenomenon, an electric phenomenon sending electric pulses, very standardized electric pulses, which are very different from what circulates into electric cables we make. Because it's more like a quadrupole circulating, like successive polarization, depolarization of the membrane. And then it comes to the dendrites of the other neurons. And if you have enough currents incoming, then the neurons sends information to the other one. So they communicate like this, and you have some organization. And a curious phenomenon is that throughout your life, for example, you breathe without even stopping, because if you stop for too long, unfortunately, you die. So you can see that here, this is a recording of some neurons in the brain. And here, it's a recording of the movement of the diaphragm. So the muscle that makes your lungs breathe. And so you can see that you have a correlation and you have periodicity. So your neural network needs to maintain this periodic behavior for you to stay alive and for many key processes in the brain. So you have, and these periodic processes, which are autonomous, so they don't require input, are found in the visual cortex or factory cortex, in the hippocampus, which handles the memory, and they can be quite fast. So gamma range is 30 Hertz. It's considered you have different frequencies in the brain, and gamma is considered to be one of the fast ones. And what's peculiar is that you don't really need a neuron that intrinsically oscillates. You do have neurons in the brain that intrinsically oscillates, and so they make other neurons around oscillate. But you have also part of the brain where none of the neurons oscillate, and the neural network composed of thousands, tens of thousands, millions of neurons oscillate in a synchronous way. And so a good question for mathematicians is, how can you have a collective oscillation from single units with the same rules? And for that, you can start with one of the simplest yet reasonable integrate and fire models, which is used since more than a century. So you have now more fancy models. The problem is that they are computationally intractable. So with this one, you can get a rough understanding, which is often good enough to capture phenomena. Where you look at one typical neuron, for example, in the network, and you have its voltage. Cm is the capacitance of the membrane, and if you disconnect it, so if you remove this I, which is the incoming current on the neuron, it will just relax to some equilibrium voltage, which is VL, the leak voltage. Leak because just your electricity leaks to this point. And so imagine now you put a little impulsion, then you go there, and if nothing else happens, it will relax to the leak conductance, which is about minus 70 millivolts. And if you have in this incoming currents a lot of electricity coming again and again and again, then you go through this threshold there, and then it jumps. And this is a very stereotypical jump. So in the model, what we say, we start there, then if it gets to this point, then you put it back there. because you know that there you have some other mechanisms coming in. And so this current is through the interaction with all the other neurons. So at each time for each connected neuron, so this is a sum of the neurons connected to the one you are looking at, and this is a sum for all time, for all impulsions coming. So this is still too complicated for proper mathematical analysis, and it's very hard to simulate because these times can be stochastic, so you have to decide which law, etc. So what people in probability do, and like, don't ask too much questions, because if my understanding of what they are doing is very sparse, to say the least. They assume that each neuron discharges with a Poisson intensity and with independence that they precisely defined. And so they replace the incoming current by something, by a process which has the same mean and variance in the large number of particle limits. And so they get, for the voltage, here, these stochastic differential equations. And then these stochastic differential equations is associated to PDE. And what I study is the PDE associated to this. So if you write it, it writes like that. So it's a parabolic PDE with this coming from the Laplacian there, from the Brownian motion there, sorry. And you have this flux. So it's a Fokker-Planck equation, and you have this flux where you have the firing rate, which is the effect of the other neurons discharging. And if you apply conservation of mass, because you don't lose any neurons in the process, you find that the firing rate must be the flux of neurons crossing the firing threshold VF times the diffusion parameter, which is sigma squared over 2. And so and then you reset. So what you lose at the right hand of the domain, you get it back at the reset point, which is the resting potential. And here you have the leak factor, that if you disconnect the network, things will just relax to 0. So 0 is not a real value. It's just like when you study mathematical system, you rescale to get 0 because it's easier. And you have this boundary condition where you have no neuron past that, so you kill them, and an initial condition. And the system is not easy to study because of this non-local structure, because what happens at the end of the domain, at the right end of the domain, has an effect on all the domain. So you cannot apply straightforwardly the classical tools for Fokker-Planck equations, and you have to be a little bit careful about what this thing does. So first, let's look at stationary states. You can compute them quite explicitly, not really, because you can see that in the formula, you have this red term, and this red term is defined through this fixed point functional. So don't look at the very details of the formula. Just the idea is just that this is a Gaussian. This is a term which is there to account for the boundary conditions, the reset conditions. So this is technical, and this is a fixed point equation for n infinity. And so depending on the number of solutions, so this is a real number, and this is an integral. So it's just a real function, like a real function, and you look at the number of fixed points. And depending on the number of fixed points, you have 1, 2, 3, I don't know, no stationary states. So they were classified. I won't go into all the details about their classifications, but the most important thing is that if B is negative, so B is the coefficient which is there, which says that the networks is inhibitory, excitatory, strong inhibition, strong excitations. So you can see it's defined like this. So number of neurons, strength of the neurons, number of the inhibitory neurons, strength of the inhibitory neurons. So if you have strong and a lot of excitatory neurons, B is positive. If you have a lot of inhibitory neurons, or they are very strong, B is negative. So basically, this B is just telling you what the network is doing. Is it mostly exciting itself or mostly inhibiting itself? And inhibition can be very important. Like so, when B is negative, you have a unique stationary state. And when B is positive and small enough, you also have a unique stationary state. And when B is larger, you can have two. You can have no stationary state and maybe three, but that we don't know. I don't think we know if there are cases with three. We know that you have cases with at least two. So this system was the local existence was performed by José Antonio Carrillo, Maria Pia Gualdani, and Gonzalez and Schoenbeck. So and the technique is it's not that easy. You have to change variables to rescale it to a free boundary Stefan problem, and then apply all the methods that people in free boundary problems have developed. And you derive a fixed point for the firing rate, n of t. You solve for the firing rate, and then the free boundary is known. And then you have just a heat equation on a domain with a varying boundary that you know what it is, and then you can do this change of variable in the other direction and get a solution, a local solution. When B is negative, this method also gives you that the solution is global in time, uniformly bounded, and as smooth as it can be, because you have a direct delta mass in the equation. So at this point, you cannot be smooth, but away from this point, you are smooth. And you have this blow-up phenomenon when B is excitatory, that I won't talk too much about because it's the subject of the next talk by Maria José Cáceres. But so well-posedness for this system is a little bit challenging, and you can have, in the excitatory case, you can have some strange effects, but I will mostly focus on the inhibitory case. And when B is small enough, it is proved that you have convergence to a steady state. And I will first talk a little bit about this because it's interesting from the mathematical viewpoint, and also because when you have convergence to the steady state, you don't have periodic oscillations. And the motivation of my talk is to study these collective mechanisms of oscillations. And I will come back later, but for this model, you don't have periodic solutions, at least they were never observed numerically. So we will complexify the model a little bit after that to try to find them. So first about desynchronization, which is convergence to these stationary states. So it's not obvious what these stationary states mean. Yes, it works. So yeah, so you're looking at the distribution P of Vt of finding a neuron at potential V at times t. So if this is stationary, it means just that the distribution doesn't change and no information is conveyed. So basically nothing happens and the network is in a resting state. So it's why we call it neuroscience, it's desynchronization. And so what this result tells you is that if the connectivity is not strong enough, just information is lost and then the neurons go to rest. And what you do is you apply this relative entropy. So now this horrible formula is there. Probably most people are checking their emails. So I will remove these horrific terms very fast and just write this. So basically you have this, which is decay, and you have this, which is annoying. And this, you might guess, is a relative entropy. So which is a classical tool in Fokker-Planck equations. So for linear Fokker-Planck equations, it gives you exponential decay to the stationary state with quite little effort. Here you have to provide more efforts because of this. And how do you do this? You want to control this. This is a firing rate, and this is a connectivity parameter. So first, you will need B to be small enough, because in nonlinear PDEs, most of the time, it's very hard to do anything if the nonlinearity is too big. And you need control over this. And what you need is an L2 estimate, because when you will do a grand val, let's say this positive stuff can be expressed in terms of this, you will have a grand val and you will have an integrator of things there, and you get a squared at some point, because square are like quite common in math. And so you need, yeah? No. No. Yeah. It's a battery. Yeah. So it works? Yeah, perfect. So yeah, so you need basically for technical reasons, you need an L2 estimate on this thing. And then you are like, now what do I do? Because it seems even worse than doing things for the initial equation. But in fact, you can just apply the same method, which is computing, again, a relative entropy. But now you want to get closer to the boundary because the firing rate is what crosses the right hand of the boundary. So your idea is to, a naive idea would be to compute, to take a cutoff function. So this, let's imagine this is just like a cutoff to look at what happens close to the boundary, then to put the stationary state there and compute the derivative. Problem is that it doesn't work. So what you do is that you compare not to the current stationary state, but to the stationary state for another parameter. This way you can get uniform estimates. So you fix another parameter, B1, which is not B. And then for the solution associated to the parameter B, you compare to this B1 stationary state. And the advantage is that as long as what you do is B invariant, you can send B to, you have more freedom of movement to get something. And so the idea is that you compute the derivative of this and you get something like this, where this functional f does not depend on B. It depends only on the B1 and on the firing rate for the stationary state associated to this one. So it's an entropy method, but comparison to another stationary state, that the current one. And this works because you basically, so without like writing, because the expression of f is complicated, it changes depending on the sign of B, etc. But just if you have like derivative of I equals minus n squared plus things that are bounded, and you can prove that I is bounded, then you just integrate between 0 and t, and you get an integral of n squared, and it's bounded, and so you get something like this. So yeah, so I think basically it's all the core ideas there. It's just there, then you apply the technicalities, and so you can look at the nice article from so Carrillo, Pertam, Seller, and Smets in 2014, which develops and applies this methodology. And so they get this this nice theorem with technical assumptions related to the successive application of the entropy methods. You have to get the initial conditions meaning, so they have to exist, etc. You get basically the relative entropy for the special choice of this convex functional tends to 0. So it's bounded by an negative exponential times the initial condition. So you have decay to in a weighted N2 norm to the stationary state. So numerically, it's this, and the stationary state, the distribution in voltage of the stationary state is like this. So this is the Boring, so with big statuic here, 0.5. So this is the Boring case. And the problem is that what this model do is basically going back to the stationary state or blowing up sometimes in the statuic case. And we want oscillations, so we have to change a little bit the equation. And there's something that we didn't take into account, which is the fact that when these guys cross the boundary, they send electric signals, but electricity in neurons is not like electricity in human-made cables. It's not going to the speed of light. In fact, it's not, I won't say slow, but not as fast as you might expect. So for big animals, for example, like whales or elephants, it can take even seconds to go from through nerves to one end to the other of the animal. So you have to take account a small parameter there, d, which is meaning that when a neuron fires, it takes some time to have an effect on the rest of the system. And so this is a little bit more realistic, and it changes dramatically the qualitative behavior of the PDE. So now you need this new initial condition, because otherwise this doesn't make sense when t equals 0. And so you have P0 and 0, and you perform the same analysis. And so here are numerical simulations. So in two cases, one case, two cases, so different set of parameters of the solution of the system. In the inhibitory case, and you can see this is a time lapse. So a time later, and then it jumps back to there. And this is the firing rate in time. And here you have other parameters. So you have stronger signal from outside the system. You can add a parameter, like you can change VF, which means that you get it gets easier for the neuron to fire, and it just means that you have excitatory input from outside, and then you get a more clear, like a periodic behavior, and you have a sharper evolution of the firing rate. But what's interesting in this case, when you are away from the boundary, is that this is a Gaussian, basically. So it looks really like a Gaussian, and in fact, it is. When you look numerically, it's very, very close to a Gaussian, a moving Gaussian. So first, so I've studied first some years ago with Maria José Caceres, Delphine Salor, and Ricarda Schneider, the basic properties of system. So global existence. So if you choose nice initial conditions, so by nice I mean like 5 awful properties. That means that your derivative to the right hand of the domain, to the middle part of this, but basically it's just like PEC1, basically. And in C0, you have a strong solutions, again as strong as you can get with the direct mass in the middle of your domain. So if you are away from that direct mass, you are C2 in a space, C1 in time. If you are on the direct mass, you have like matching properties of the derivatives, but basically something quite smooth. And we took the proof I explained to you above, and we patched everything that fails, basically. So it's not straightforward, but it's not interesting enough. So I would focus more on this. So I prefer to explain it to you in the simpler case where you really see the mathematical structure. There it's more like nasty details about how to integrate from 0 to time and get rid of the delay, but you get the same result. Just now, your constant stuff contains not only the entropy, the relative entropy of the initial condition, but also some kind of time relative entropy of the initial condition in time. So of what the firing rate does before 0. So we get a more complicated things, but the core ideas are quite the same, and you get exponential decay when the connectivity is small enough. So these periodic solutions we observed in the numerical simulation must be for B not too small. And we had another result, which is a non-existent result for periodic solutions, that if B is positive and too large, then you have no periodic solutions. In fact, if B positive, I don't think anyone observed periodic solutions, even with the delay. So now we will focus only on the case with a negative connectivity, which is even more puzzling because you have all neurons or most of the neurons are inhibitory, or in your model, all neurons are inhibitory, and yet you have self-sustained oscillations, which is quite strange how you can get a collective mechanism where everyone is trying to dampen the activity. Yeah, and so we come back to the question where to find the periodic solutions, and now we are reminded of the Gaussian shape we observed in the numerical simulations. So let's look for periodic Gaussians. So when the wave is away from the boundary, you have no one crossing the boundary. So basically your firing rate is very small. So this delta Dirac term times the firing rate, let's neglect it. and then we put it into a remainder term. So it's just a formal writing. Let's assume you have phi, a solution of this equation. If you write p equals phi plus a remainder term, then the remainder term must satisfy this. And then you can extend your phi to infinity, and you just take a remainder term which is negative after Vf to account. So you have R, which can be negative or positive. And you have now a simpler equation in the whole domain in R. And if you do this, you can solve for phi, and you find that this phi must be a Gaussian. So you just have to simplify the equation a little bit to get to see the Gaussian solution. And when you look at the numerical simulation, the variance is a good one where you are away from the firing rate. And we find this condition for the speed of the wave. So let's see numerically if it's plausible. And you can see that in the top case of the previous simulation, the residual term, the remainder term, is not 0, but it's 0.01, and the solution is of the order of 1. So actually, it does capture something, that the remainder term is small, and so basically what we simulate there with the dashed line. So solid line is the solution. Dashed line is this thing with this speed. And so we input the firing rate of the PDE solution. And you can see that it matches very nicely. In the second case, where it's a little bit more singular, it's more 1/5. It's not 1/10, it's 1/5 of the size of the solution. So you have a less clear match, but yet you capture the oscillating behavior. So, but the problem with this approach is that it's still a strongly coupled system, and it's very hard to prove any smallness theoretical result for this R. At least we have partial results, what we put in the paper, like conditional results. If you assume that N behaves like this, then R tends to 0 in L2 norm of things, but we don't have a definite answer. So what we did is to simplify it again, just to change the system to see if we can get something on a toy model. And so now, let's say that this firing rate, so in the previous system, you can see the firing rate there is a sum of what crosses there and what crosses there, because it's the derivative of this at the boundary, so sum of the two. Let's now imagine that the firing rate comes only from the Gaussian wave. So we neglect the firing rate that comes from the remainder term. And so now, just the equations are decoupled, and you don't have any remainder anymore. And you have a closed PDE system, which is why you don't have the rescaling mechanism, because you don't have boundary now. So you lose nothing, so you have conservation of mass for free. And you still have the firing mechanisms. So this is a little bit less realistic, but for this, we can perform a precise mathematical analysis. And we have this result that if you define this Gaussian and you assume that this scalar function of the time satisfies this delayed differential equation, then this is a solution to the system of PDE, so to this system. The problem is now that to prove that there exist periodic solutions, you have to prove that this delayed differential equation admits a periodic solution. So just take my time. Yeah. So we are reduced to this problem. And for this problem, you have a lot of tools in the community that studied delayed differential equation for the last 50 years. And we applied these tools to prove this theorem that if your connectivity is negative enough, and if your delay is large enough, then you have a periodic solution, which means a periodic solution for the simplified system of PDE. And how we do this, we apply this marvelous thing, which is a Broder's fixed point theorem that I didn't know about before doing this research, which is an extension of Brewer class. Not really an extension of it, but it's in the flavor of the Brewer fixed point theorem. But under this like standard hypothesis on the domain, you have at least one fixed point that is not adjective. And the definition of adjective is that you don't send away all the close points by applying the functional, by applying the function. So basically, this means that adjective means you can start as close as you want to the point, it will get out of your neighborhood. So what the theorem says is that under this hypothesis, so convex bounded subset, compact map, continuous, etc., you have at least one fixed point that in some sort attracts solutions, or at least do not repel them. And so what can you do is that prove that the stationary states in some parameter ranges eject solutions, eject closed solutions. And so you must have something, if you construct a functional f such that the fixed points are either periodic solutions of stationary states and stationary states eject solution, then you have something that does not eject solution, which is a periodic solution. And so we study the stationary solutions. We study the eigenvalues. So you can express them in terms of the Lambert function. So you can, you can get a lot of information, and you can see this necessary condition, which translates basically to B has to be negative enough, which is in accordance to the fact that if B is too close to 0, you converge to the stationary state and nothing interesting happens. Then you define your functional f. Well, we have a little bit of technicalities. We have to change a little bit the problem, take a cutoff, etc. And then we come back to the general problem, which introduce the annoying VF greater than A squared assumption, but it's not a huge loss. And then you prove that periodic solutions. And now we want to compare these periodic solutions to the original solutions of the original system. So, I mean, before the simplifying assumption. So you can see that it's not perfect. So right, you have the fine rate. Left, you have the position of the highest point. So basically, the first moment. You can, yeah, basically, I don't remember. You have two choices which are very, very close to take the first moment, so the average, or to take the highest point, the maximum point, and both are like very close at all time because it's close to the Gaussian. And you can see that the DDE solution, which is C of t, is quite close. You just have a little shift in phase. You lose something. And in the more singular case, you lose a little bit of depth because of the term you neglect, which are the boundary and reset term. But you can see that this captures the mechanism. And it's a good news because it's very hard to understand what happens in the PDE, but to understand what happens in this different delay differential equation is simpler. So now you can study the over-analytical properties of the delay differential equation and be confident that they help to unravel a little bit the inner structure of the PDE and why you have periodic solutions in the PDE. And so it was the next step of the research is to see asymptotically when the connectivity tends to -infinity, what happens? So that the mechanisms will be clearer because you sharpen things. So it's more an experience of thought to say, let's send the parameter to infinity to see in the limits what happens and to hope we get a clear picture. So we rescale things. So log rescaling, which is something that works nicely in many cases in asymptotic analysis of differential equations. And you get this thing, and it seems that it's worse than the differential equation we had before, but in fact not, because here you have an exponential of the present plus a function of the past. And as the parameter tends to infinity, beta tends to 0. So the past is a shorter and shorter period. T minus beta tends towards t, and 1 over beta tends towards plus infinity. And so you have the stationary state of this thing tends to 0. So now you can decompose your dynamic into when u is, so now u will be basically between 0 and 1. And when u is very close to 0, this term is dominating. When u is very close to 1, this term is close to 0, and this term is dominating. So you have when the present is dominating and when the past is dominating. And we can prove this nice result that asymptotically, when beta tends to 0, which is b tends to minus infinity in the original problem, the solution, and this is all solutions, not only the periodic solutions, all solutions converge to a fixed explicit profile. So P of t equals 1 minus t, and then P of t equals Cm plus 1 minus t, and then periodic. So basically, these are straight lines like this. So you go from from Cm, sorry, just that the initial condition is 1, so you first go from 1, you go to 0, then you jump instantaneously, and then you go to 0, and then you go to 0, and then you go to 0. In this rescale variable, of course. So and basically, that's what happens is that when the solution is high enough, you just decay, because the 1 minus the thing is large enough so that the past term dominates, and then you just decay, and we have this lemma that says you decay asymptotically in a straight line way. So we have a lower bound and upper bound. And then you get low enough, so close enough to 0. And when you do this, the over term enter into play. And then you have another lemma that says, if I go below this line, then I know I will go to this uniform constant in a short time, in a time t1. And then at some point I know I'm bounded by 1. At some point I will decay again, because I can use again lemma 2. And then I decay, and then I repeat, and then you have a lemma 4, which is not written, which is stability, that you always jump asymptotically to the same height and not to different height each time, which you could have a chaotic behavior, but you have a local stability result that if you start with 2 initial conditions close down there, you end up with a close position up there. So you always jump to the same value. And lemma 5 is just to prove that all this time tends to the same value, so you have periodicity. And so basically we can write lemma 2, so you can remember this term, which was the first term there. So you have 1 over beta, beta tends to infinity, so this tends to 0, because 1 minus e is negative. So minus 1, so this tends to minus 1. So decay, linear decay, and then exponential growth, because you have exponential. You can choose a fixed epsilon small enough such that you have this lower bound when in the past you are small enough, and then you go up exponentially fast. And we had an exponential rescaling. So it's in original variable, it's going back, it's going down, exponential of exponentially fast. And going, and this one in original variable is exponentially fast. So these are numerical simulations to show the solutions. And so basically what happens for so what it tells us for the original problem is that what happens is that you have your domain like this, you have your Gaussian solutions like this. If you have a strong enough negative connectivity, when neurons cross the boundary, all the density is propelled very fast to the left, to negative potential values. So at the next time, you have this. But now the firing rate is very low. So it's the term dominating is just the Fokker-Planck term sending you back to 0. And so you come back at exponential speed, which is the speed of exponential decay for a linear Fokker-Planck equation. And then you come back close here, and then you go back again. And it's what the delay introduces, that if you don't have the delay, you just oscillate less and less until you stabilize to the stationary state, which exists and is unique in the negative case. So basically, the conclusion of all this study is that it's really a thermodynamical mechanism, that you always have some neurons close to firing, they fire, then they send all the density away, and then the density just comes back for thermodynamical reason, and then it happens again. So it's why in the observation by neuroscientists, none of the neurons oscillates. All the neurons fire sporadically, but globally it oscillates because you have a feedback mechanism, a feedback loop. So yeah, so we have still a lot of questions because existence of periodic solutions for the original PD system is still open. So probably one of the best tools would be to use the theory of Hopf bifurcation. Problem is that since the PD is singular, it's hard to do it because you have to compute the spectrum of something, but why and how, and so there are a lot of work to do. Another road could be to prove that R tends to 0 when B tends to -infinity, but this is hard again because you need uniform estimates on the firing rate, and you need to prove that the firing rate tends to 0 uniformly, or in L1 norm or something, when B tends to -infinity, which is also very hard. You can prove that the firing rate of the stationary states tends to 0 when B tends to -infinity, but it's a very hard problem. At least we have no idea about how to do it for now. Then you have the excitatory case with the delay, because as I said earlier, you have global in-time solutions with delay always, never blow up. So what happens in the excitatory case if you don't have periodic solutions? So Maria Jose Caceres will try to answer that in the next talk, and then finish the study of the non-delayed model, because periodic solutions were not observed, but we know about convergence to stationary state only when B is small enough. So when B is negative and large enough, so you don't have blow up. We know from numerical simulations that you converge to stationary state, but we don't know about any method able to prove it. And that's all for me.
Thank you for the nice talk. Any questions?
So I'm not sure I understood why your solutions are discontinuous, your P, because it satisfies the delay equation. So how can it be that it is discontinuous?
It's discontinuous because of the rescaling. Because what happens if you don't rescale, you go to infinity. So you have, if you don't rescale, you are between 0 and 1. If you don't rescale, you are between VF and -infinity. So you have VF there, and what the solution does is that it's close to 0, then it goes really fast there, and then it comes back exponentially fast. And the problem is that this phase there is way faster than the exponential coming back to VF. And when you rescale, basically this very fast phase, you go to even, so to get a clear thing, basically you have a length there, which is, I think, like B to the power, to some alpha between 0 and 1. And so when B tends to -infinity, this periodic solution that does this, it gets deeper and deeper to infinity. So when you rescale something that goes to infinity between 0 and 1, you lose this going down part, becomes singular, it becomes a straight line. So basically it's just that you take this thing and you prevent it, you fix a boundary there and you rescale to not go to infinity, to just go between two values. But so if you go faster and faster between two values, asymptotically you go in a straight line. And then the exponential decay, because of the logarithmic change variable, becomes a linear thing. So it does this. And then we put it in positive because it was easier for technical, like it's easier to work with positive numbers. So instead of this in negative, we just shifted it, put a minus in front of it.
Ask another question. Okay, and so in your approximation, where you neglect, you have two levels of approximation.
Yes.
In some sense, if we want to prove, okay, can you justify a small parameter compared to the real problem, to the true problem, to justify that? Is there any way to make an error estimate with the reality?
So yeah, so there are two problems. So you have two challenges. The first one is to prove in this original equation. So this is the original equation, basically. Just you would change its structure, but it's the original equation. So to prove that this R tends to 0. And this is less hard. We can do it at the moment, but it's less hard. We have a conditional result, which is if n there tends to 0 when b tends to minus infinity in L1 in a weighted L1 norm. So it's not very strong. Just firing rate tends to 0 in L1, then R tends to 0 in L2. So proving basically this result, that these two curves, the dashed curve here and the solid curves are close, asymptotically they match. So this is not hard to prove. Well, not hard. Too hard for us at the moment, but it's achievable, I think. You have to work on the firing rate and to derive some uniform estimates in B. The second approximation is to say this does not contribute to the firing rate. And this is way harder. Why? Because you have B times N. So it means that if you want to say, so when you compute the firing rate there, the problem is that you don't have the firing rate, you have B times the firing rate, and you are sending B to minus infinity. So you get firing rate B times firing rate equals B times this firing rate plus B times this firing rate. So now you don't need R small, you need B times R small when B goes to minus infinity. And this, we don't even know if it's real. Maybe it's false. Maybe it's false because when you look at the, no, it was not this one. It was, yeah, this one. This one. When you look, you have this discrepancy there. And numerical simulations are not able to provide an answer to what happens for very negative case because just the scheme dies. We can push the scheme to B equals minus 100, minus 200. Past that point, it dies. Just it cannot like you lose. You can see that the solutions lose crucial properties. So maybe it gets worse and worse. So maybe what we neglect there in the second approximation is false. But what gets better when you do numerical simulations is shift. So you can see you capture well the period. So I think the mechanism is well understood now, but we don't have a clear enough understanding of the mathematical structure to have a full result like this converge to 0 and this not. So and the interesting thing also with this rescaled system and the idea to study the delay differential equation is that you can take in the delay differential equation you can take B equals minus 5 million and the simulations runs perfectly well because it's just scalar equation. So it's also the advantage you can simulate it you can get a lot. And this result gets you, when you take the change of variable in the opposite direction, you get a lot of information about how the period evolves, how the depth evolves, etc. You have asymptotic terms, like the period evolves in logarithm of B, like a constant times logarithm of B. The depth, as I said, in BO of B to the power, absolute value of B to the power something between 0 and 1. Basically, in fact, to the power Cm. This Cm there is the power of B for the evolution of the depth. So we have now a full understanding of the delay differential equations. The challenge is to find if yes or not we can relate it rigorously to the original system.
Other questions? Okay, if not, let's thank Pierre again for a nice talk. We'll resume at 4 o'clock, so 40 minutes break.
Thank you. Oh.
Mm. 45 minutes, exactly.
Oh, wait, okay, we have a big break.
Yeah.
Okay, I thought I was like 45 minutes in advance.
No, it's just that the question thing, we didn't use 15 minutes of questions. So. Half an hour break.
Yeah, I'll finish this earlier,
Yeah, you used 45 minutes,
Yeah.
like on the dot almost. So.
which I think was the most people could concentrate. So
Yeah, I started zoning out at the end.
yeah,
but
I think it was the right time to finish.
Fine.